All right, so continuing with chapter 11 and our discussion of the Jovian planets, we've been talking about the characteristics of the worlds, and we talked about everything up to the semi-major axis and the way that the planets are staggered in their distance from the sun and how that staggering gets bigger and bigger. They become more widely spaced apart. We also have their rotation periods. I think I started to say that they're all pretty fast. And so this is not what you necessarily would expect because you might think that these really big planets are too big to rotate so quickly. It turns out that the opposite is true. The fact that they were able to grow so big and that involved taking in so much gas, pulling in all of this gas due to their gravity, that they are rotating quickly as a byproduct of their creation. It seems to be a totally natural characteristic that they all spin real fast, especially for their size, around their axis. And so basically all of their rotation periods are less than an Earth day. The only, the negative one shows up because it's technically spinning backwards because it's tilted a little bit more than 90 degrees. But point being is, we can all see there the rotation periods are in that range of, yeah, less than 12 hours, right, for Jupiter and Saturn, and then between 12 and 16 hours for Uranus and Neptune. And because I'm just looking at these and looking at them as, a fraction of a day, and then remember, 24 hours in a day, because that's, of course, the period of time we're talking about here. Tilt or the orbital tilt, Jupiter doesn't really have one at all. It's one of the most straight up and down planets. The only other planet in the solar system that has a similar tilt would be basically on the other end of the spectrum, the smallest, which would be Mercury. So because Mercury is almost, its axis is almost exactly vertical relative to the ecliptic plane, just like Jupiter. Saturn, almost like an Earth-like tilt axis. Then we have, the very strange tilt of Uranus, and then a Saturn and Neptune kind of having comparable tilts. So lots of tilted planets. It's kind of a common state that ends up. It really isn't surprising at all that so many planets are tilted. If it just crossed your mind, like, what? Why are so many planets tilted? What's going on here? What's it? Why do we have a bunch of planets that are kind of like on their side? Well, because this all comes down to these, like, the physics, right? All these planets are created because there's this spinning giant cloud of gas that collapsed into a giant spinning disk of gas, and then eventually mostly coalesced into the sun, and then the leftovers coalesced into the planets, or accreted is the term we tend to use, right? The accretion of matter. By the way, sometimes there's a synonym, which is the amalgamation of matter, although your book doesn't tend to use amalgamation, but instead accretion. So, but if you ever catch me saying that, that's what I mean. But the tilts are like, well, I mean, think about like when you spin something. If I get like a top, like a children's toy top, and I spin it, it's unlikely that I'm going to spin it so that it's exactly vertical. That would require a surface that would support exactly vertical spinning. Probably have to have some sort of notch in it, and it would require me, turning it just right, giving it that initial twist so that I didn't, accidentally tilt it when I started it. So most of the time when I start a top spinning, I'm going to start it so that it's tilted a little bit, and then it's going to precess. That tilt of the top is going to move in a circle as the whole top spins much quicker than the precession rate. And that's the deal of planets. It's just much more likely that as everything comes together, just like, when the initial twist that you give the top is like the initial conditions of all the matter, sticking together, all the planetismals colliding, and those generally are going to come together kind of not exactly lined up. So then you're going to have a top, and the planets act like tops. They precess. I know that there's a question that some of you, I'm sure, have seen on the test about precession. And, it's in the book. We didn't cover it that much in the lectures. It was one of those little topics that slips through the cracks, but definitely in the book. And if you haven't, there's a hint for you. So we have lots of precession in the solar system, lots of planets acting like toy tops. Okay, so that's it for the summary of characteristics. Now we're going to get into their interior, starting at the very inside and working outwards. So there's a lot to say here, and I know that in the other class I probably spent too much time on it, but now I kind of know what to expect. So I'm just going to try to just quickly get to the key ideas. So each of the Jovian planets has a rocky core. So they all have a rocky core, which is shown here as this weird little cone. And why is it shown as a little cone for all of them with this number next to it? Well, the reason will become more obvious because we're essentially going to be, and this is based off a figure from your book, if it looks familiar, but we're going to be working our way out. So this little cone is going to become much bigger and represent like a cross section, or at least a cross-sectional cone that slices into the planet. And so far, it's only covered the core, which is why it's relatively so small. The numbers are based off of a comparison to the entire planet Earth, and they're rough estimates of thousands of kilometers. So Earth has an entire size of about 6,000 kilometers. So the six represents that. So it's a unit of sets of 1,000 kilometers. In other words, Jupiter has a rocky core that's about 7,000 kilometers in size, Saturn, 8,000 kilometers, Uranus, also about 8, and Neptune, 10,000 kilometers in size for its core. In all cases, they are rocky, which is why we're comparing it to Earth, because Earth is rocky all the way through. Sure, Earth has layers, right? We talked about Earth's core, and we talked about it being, being a largely iron core, but collectively, what is Earth? The terrestrial or rock planet, right? And so are the cores of the Jovian worlds. When we say rock, that's just a kind of a catch-all. It includes metal. Okay, so it's rock and metal, and some mixture of the two. So this is, by the way, just showing the size, and that is going to be the main focus. Just once, I'm going to point out that the size isn't everything, and the fact that Jupiter has the smallest rocky core is not saying that it has the least rock. In fact, the I just remember this number from teaching from a different book actually years ago, that this core, although being almost the same size as Earth, as we can see, right? The difference is 6,000 versus 7,000 kilometers in radius. The mass of these two, rocky spheres, entire Earth or core of Jupiter, is totally different. And Jupiter is 10 times as massive as Earth. And why so much more massive if it's made out of the same stuff, rock and metal? Because it's under such high pressure that it's just a incredibly condensed version of rock and metal. So it is a super condensed solid of rock and metal, where it would be in a liquid state due to the very high temperature, but it's then forced into a solid state because of the very high pressure. And so it's able to have 10 times the mass that you might expect, because of that. And that actually might make Jupiter's core the most massive, although Neptune's being bigger and also fairly compressed, it'd be a close matchup, and I don't have the number handy. We'll hear more about the cores in a second. Okay, so there's Earth for comparison. So notice, right, all the Jovian planets have this rock and metal core, in each case bigger than Earth. Okay, and so if we took their characteristic images, these flyby pictures that show the entire gas giant, and kind of had them represent the core size, then this would be another way to compare them. So here you have to just like look at Earth and compare it to these various brown dots, right? Which are scaled. You can tell that Neptune's is bigger than the other ones, but it might be a little tricky to appreciate the scaling. And so that's what this image is doing: is Jovians, right? The Jovian planets scaled to the size of their rocky cores, and then compared to Earth. So this represents Neptune's rocky core, Uranus, Saturn, and Jupiter, respectively. So when we talk about the volume, good reminder, and I've been saying this just recently, that the volume is proportional to what relationship of the radius. When we go from radius, which is what we've been talking about so far, and we want to actually get a number for volume, what math do we use? Go ahead and let me know. Max will ask a question. Let's see. Why is it that whenever there is a picture of Uranus, most of them don't show the rings? Yeah, so some of that's probably just like kind of what authors are used to doing. Um, yeah, because Uranus does have the second most visible rings. We'll soon learn that all four of the Jovian planets have rings. The only one that's easily visible in the visible spectrum is Saturn. And so that's the only one that we regularly show. But I know that one of them is also faintly visible, and I believe it is Uranus. So you will see it occasionally. I'm sure people find that kind of having a image of the planets that is easily recognizable. But if we start showing a ring for Uranus, and then you know like people like will doctor the image to maybe make the ring look brighter than it actually is, and then so we're creating unnecessary confusion if we're making it look more obvious than it really is. So it's more like kind of this like follow-up factor. Say, hey, they all have rings, but basically only Saturn's is easy to see, and so we're just in the habit of always showing it. So that's my explanation. I don't know if it's satisfactory or not. All right, everybody got it. Good. It is the radius cubed. Volume is proportional to radius cubed. All right. Wasn't it just yesterday when I misspoke and said squared? Someone pointed out, it's cubic relationship? I'm like, yeah, I meant to say. Yeah, there's the proportionality. So with that in mind, we can just go ahead and say, okay, hey, we can take the volume of Earth in this unit of 1,000 kilometers and cube it to get 216, right? So I guess that'd be 216 thousand kilometers squared, but you have to, or cubed rather. There you go. And so if you actually wanted to convert it to 1,000 kilometers, that's in parentheses, and so it's sort of a strange unit, but that's why we're just thinking of it as just a number for comparison. And then we did the same for Jupiter, 7 cubed, 343, and then 8 cubed in both cases for Saturn and Uranus, because they're both comparable. And then finally for Neptune, 10 cubed. That one's easy because we're familiar with scientific notation, how cubing 10 is just about moving the decimal place. And so, of course, 10 cubed just becomes 1,000. And so then we can take these volume numbers and compare them. And when we take 343 divided by 216, we get about 1.6, 512 over 216, 2.4, and 1,000 divided by 216, about 4.6. So what that illustrates nicely is obviously an idea that many of you understand because you got the last question correct. But still, I think it's good to see it, right? Is that when you have what looks like a relatively small difference, right? A radius difference of 6 to 10, well, it shows up as a quite noticeable volume difference. And so it always behooves us to remember that, comparing volume is a very different story than comparing radius. Good. I'm surprised, but I'm happy that it's satisfactory. Happily surprised. Happily surprised. So here's the question of the day. The largest rocky object in the solar system, based on what we were just talking about, what is it? Venus, Earth, Mars, Ceres, the core of Neptune? Or do you give up? Comparing all the rocky objects in the solar system. Get at least one more answer. So far, we got Elizabeth and Maria. Just one more. Hey, thanks, Kylie. All right. So, based off the three votes, the most popular answer is Earth, but this is meant to be a tricky question, make you think, because it's not Earth. It is the core of Neptune. Why is that? Right? Well, rocky object, not rock, not terrestrial planet. If the question was terrestrial planet, then it absolutely would be Earth, right? Earth is the biggest terrestrial planet, both in volume and mass. But as we saw, check it out, right? Neptune has way more volume of rock, 4.6 times the size of Earth. That still counts as an object, right? So the largest by size, right? And again, I think maths would be an interesting question. So I would love to follow that up, but I won't realistically. So just think about that. Right? And I mentioned the density, but still, clearly for size, Neptune is the biggest. Make sense? It was totally meant to be kind of like a trick question too. Kind of cool. It's like, oh yeah, yep, oh yeah, we love trick questions. It's like it's like this. They're fine, right? And they do make you think. They're also like this weird byproduct of teaching because what's the most interesting thing for teachers, right? Is like a question that makes them think. And so we have this bias. I literally do try to avoid it, right? That if a question seems like really interesting to me, like that isn't necessarily a good thing, right? Because that means it might be too tricky. Um, but other times they're good because they can make you think in the right way. And I think that this one definitely serves that purpose, where it's like, yeah, it's just the right amount of a trick question, just the right amount of trick in the trick question. Okay, so we'll continue a little bit more, just checking the time. We can definitely get through more of our Jovian planets. And we're going to move away from the cores, right? So that was it for just talking about the cores themselves. All the cores are rock and metal. They, kind of similar composition to the whole planet Earth, right? Or all of Mars for that matter. It's like in other words, they all have like a terrestrial planet that they swallowed inside, and because they formed under the same mechanisms, all the Jovian planets formed by planetismals crashing together, and they just were able to keep growing. So it makes sense that as differentiation occurred and the denser materials sunk to the center, that the denser materials made out of the same stuff and essentially ends up with a hidden terrestrial planet as the core of each of the gas giants, each of the Jovian planets. So above the core are other internal layers, and these would all be the internal layers that wouldn't qualify as the atmosphere. And to kind of touch on an idea that I think I led with because I tend to when I start the lecture is what does it mean for the gas giants to not have a surface? Because they don't have a surface per se. Instead, they have a gradual change of substance. They have large gravity just to begin with. So they actually have, surprisingly high gravity, even if you're in their upper cloud layer. But then as you go down into the planet, if you like, started somehow in a spaceship that was like hovering in the clouds of, say, Saturn, and then you like started dropping down into the cloud layer, at first you'd just be passing through a pretty typical gas. But then as you went deeper and deeper, the gas would get hotter and denser until it would become a liquid. It would phase change from a gas to a liquid. It would be a gradual change. And so there's no defining point where you reach like the surface of, say, like an ocean. Instead, there's this gradient of just increasing temperature and pressure, eventually causing a phase change. And then as you continue to go down past, that liquid layer because of the higher pressure, you eventually reach layers that are either also liquid or solids. And in this case, we're just showing the solid layers that are outside of the core. So everything shown here so far would be in the phase of a solid. And the reason being because of the incredible amount of weight that's above pushing down, condensing the material into a solid. So let's look at each one quickly to see what I mean. So with Jupiter, once we go past the core, as we move towards the surface, well, I just said there is no surface, the word came out. As we move towards space, right? As we move towards the exterior of the planet, the upper cloud layer, right? So as we move away from the core, the next layer is a layer of ice, right? So this is water ice somewhat, but mostly ammonia and methane ice. And it's solid ice, but not cold ice. It's hot ice. Uh, Recently saw a video about a lab on Earth that was able to create, ice under these types of conditions and show some of its strange properties. We don't have a lot of hot ice on Earth. The only reason that it can exist here is because it's so highly pressurized that it's forced to become ice, a solid, right? Despite the high temperature, right? So a little bit H2O ice, lots of methane and ammonia ice. Um, Methane and ammonia will come up a lot. And it seems kind of strange that we're talking about, ice, and sometimes I say, oh, mostly water ice. Other times I say a mix of water ice and other types of ice, predominantly methane and ammonia. Well, the whole idea is that methane and ammonia are these other, like hydrogen-based molecules that form at lower temperatures than H2O, and they pop up a lot. They're, just really common molecules like H2O, but that, sort of like much more abundant in lower temperatures. So that's the idea that we talk about them so much, and they kind of, in a chemistry sense, they have a lot in common in terms of what they're made out of. So then, above the ice layer, for Jupiter at least, is a very thick layer of solid hydrogen. So we could really call this solid hydrogen, and that term gets used. So sometimes it is called solid hydrogen. There's at least one other name for it. But this name, calling it metallic hydrogen, is the most popular one that I've seen in textbooks. And the reason it's called metallic hydrogen is I mean, it kind of invokes the idea of a solid because we think of a metal being a solid. But also, it's important because it makes us think about, well, what's special about metals? Metals usually are good conductors, right? We make wires out of them. They conduct electricity. And indeed, metallic hydrogen, so hydrogen in a solid state, is a good conductor. It allows for current to pass through it easily. And so that is a significant layer on both Jupiter and Saturn. And it doesn't exist on Uranus and Neptune because they're not big enough to create it. They just don't have enough weight above in their atmosphere levels to compress hydrogen enough to force it into this state. Because common theme, right? It just takes a lot of pressure, a lot of weight pushing down from above to actually create metallic hydrogen. Similar to the idea of, creating really hot ice, sort of superheated ice is, something that requires a high-tech lab. Likewise for metallic hydrogen. It's a difficult property of hydrogen to study because, to build the equipment that can actually handle such high pressure and then really be able to experiment on it is no small feat, and really wasn't even attainable for decades, right? Probably, I think it started in the early 90s. Saturn also has a metallic hydrogen level, but it's not, or yeah, layer really. And it's not nearly as thick because Saturn is not nearly as massive. It hasn't compressed as much as Jupiter. That's an idea we're going to see again, is that Saturn hasn't gone through the same process of compression that Jupiter has. And and this really thick layer of metallic hydrogen really shows how compressed Jupiter has become. And then with Uranus and Neptune, they just have that methane and ammonia ice um, layer, also due to compression, but just not enough for the next layer to show up. Okay, so far, there we go. This is all the solid interiors of the four Jovian planets. With the ices, solidified gases, liquids. Okay, so in other words, they started as a gas or a liquid, depending really both, and depending on conditions. And then what are the ices? What are the molecules? As I said, methane, ammonia, some H2O. Okay, so going on to a reminder about metals. This is just completely continuing with what I said. What's up with the name metallic hydrogen? Well, reminder, what is a metal? A metal has atomic nuclei in a grid, and that's opposed to some other solids where there's not a clear grid. Instead, there's like a random mixture. And in the case of a metal, some electrons can move around in the space between the nuclei. That's what makes them good conductors, and at the very least, decent conductors. So this is the electrons moving around, right? This is one type of orientation of molecules for a metal. Here's a different one. In both cases, though, in all cases, the electrons, shown as the little yellow dots, are able to move through that lattice work of nuclei. So with hydrogen, okay, most hydrogen nuclei. Okay, so this is interesting because I misremembered when I had talked about hydrogen. So this all the more reason that I was surprised that so many of you were able to reason out the question about Venus. So just if you wonder what the heck I'm talking about, don't worry about it. But I do want to get some answers on this one. So most hydrogen nuclei are made of what? So like a typical, like a periodic table, you look at it, you see hydrogen, see it's a lightest element. You might even see its atomic mass number, which is one of the values that show up on a typical periodic table. The other one is what's called just the atomic number. So there's the atomic mass number, but also the atomic number. They're like there's two different numbers that show up. So like the atomic number is always just an integer, and it just tells you the placement. So it's one for hydrogen, two for helium. But then the atomic mass number is different, and it has to do. It always has lots of decimals in it because it has to do with isotopes and in which isotopes are common. So what would you see for hydrogen? What is inside of that nucleus? Let me check and see what answers I've gotten. Cool. Maria says just one proton, and then Caleb agrees. So maybe because I literally had mentioned it earlier. Okay. Oh, Caleb changed to three. Well, turns out you were right in the first place. It is just the single proton, and that I've absolutely found, and not just in this summer class or in one class, but is widely not known. And I get it because it seems like a rule. It doesn't seem right that hydrogen just has a proton, but it absolutely does. The typical hydrogen doesn't have a neutron. It's just one proton. That is the most stable state for hydrogen, just a single proton with a single electron. To have one proton and one neutron would still be hydrogen, because to change your element, you have to change the number of protons. Changing the number of neutrons doesn't change the element. It just creates isotopes of that element. Ideas that were presented in one of the early chapters in our crash course in physics, right? This is when our little bit when we dipped into atomic physics. So the most common isotope of hydrogen does have exactly one proton and one neutron, and that's called deuterium. the deuterium that was mentioned in the quiz, right? And has come up a couple of times previously in material in the textbook and in lectures. It's not terribly common. You know, it's a tiny percentage of the overall hydrogen is deuterium, but it's not unheard of. It's it can be separated out. It exists in certain quantities as a fraction of 1%, but it absolutely is out there. There is deuterium throughout the universe, all over Earth, and with that isotope of hydrogen, there is one proton and one neutron. All right. But with typical hydrogen, just that single proton. So that means that when you make the metal when you solidify hydrogen, you end up having a network of just individual protons. So when the pressure is high enough to have metallic hydrogen, this is what the metal would look like. So instead of having these large nuclei, you just have a lattice work of just individual protons. So the protons form into a rigid grid with the electron that each of them had now free to move around, because now there's each nucleus now doesn't have a good hold on its electron. Since it's evenly spaced with another nucleus, in fact, with two other nuclei, that electron doesn't feel like it is really orbiting any of them, and instead is just free to move around with like equilibrium force that can easily be pushed by some external factor, thus creating a current. Okay, so this is kind of what metallic hydrogen looks like, which is actually pretty cool type of metal, I'm sure, like, to study and work with. Unfortunately, impractical to create under most conditions. Okay, so we're going to take a break at this point. Yeah, yeah, nice, nice. Thank you, Caleb. If you look at the average weight, Caleb pointed out that the on the periodic table, the atomic mass is 1.007, and that's because it's pushed up a little bit above one because of the little bit of deuterium, but obviously not a lot of deuterium because this number is nowhere close to two. It's not like 1.5, right? Because if it was 1.5, that would mean that you know three halves of the population is or maybe two-thirds of the population is just standard hydrogen, and one-third of the population is deuterium, but it's nowhere near that. So instead you have this atomic mass is a little bit bigger than one. Yeah, so those atomic masses are cool. Sometimes they actually are in the middle. Like if you look at the periodic table, that's because there'll be two isotopes that are equally common for certain elements. And so that's why sometimes it's like zero point 0.5, because you really have, you know, a coin flip in terms of how many neutrons there are. But that's for at least things that are a bit heavier in terms of, like, more than 10 protons. All right, let's pause the recording and let's have my official return from break time be 9:20. So I will see you all at 9:20. All right, so continuing with our discussion of the Jovian planets in chapter 11, we're now moving on to talk about their atmospheres. So once we go above the solid layer, whatever that may be, we get to a layer in each case of the planets that is predominantly molecular hydrogen. There are going to be other elements, other molecules, but in much smaller amounts. The dominating characteristic of this layer is hydrogen, just like underneath for Jupiter and Saturn. It's because there's so much hydrogen in the universe, and it was a crucial building block of these worlds. Uh, Definitely much thinner on Jupiter. By the way, remember that all these numbers are in thousands of kilometers. It kind of gives you an idea, right? Um, Saturn, much thicker level of molecular hydrogen because Saturn hasn't collapsed that hydrogen, molecular hydrogen gas into the solid phase. And calling it a gas, right, isn't the whole story because, as I said, there's going to be some gradual change. So definitely starts as a gas, is molecular hydrogen the whole way, but would phase change to a liquid before it phase changes to metallic hydrogen. There's not some, like, solid boundary that's clearly, like, shining metal, instead it just gradually gets denser. And also totally shared characteristic with Uranus and Neptune, also big layer of atmosphere, which is molecular hydrogen. When we're talking about molecular hydrogen, we're not talking about other molecules, we're just talking about H2. So that's the diatomic hydrogen. It's the stable state of hydrogen for lower energy environments. So if it's not, super energetic, these are usually super hot, then hydrogen will stay as H2, it's a very stable molecule. It'll only split into atomic hydrogen under, extreme conditions. Those are your atmospheres. Here's the summary about the percentage of the volume of the planet that is the atmosphere. So Jupiter has the lowest percentage, as much of its atmosphere has been compressed. It's like collapsed under its own weight, essentially. Saturn, Uranus, Neptune, much more of it remains in that, largely gaseous but always molecular phase. We can definitely see the metallic hydrogen stands out for Jupiter as being a much larger percentage. The ice being particularly thin for Jupiter, although I don't know exactly why. Other than that, maybe it's too high of a pressure for it to exist. Um, but then Saturn, it thin but definitely there, and then really large ice layer, which we see proportionally, especially, right? Because you might think, oh, it's not that large compared to Saturn, but proportionally it is. So it's about a third of Uranus's volume, and nearly half of Neptune's volume is that ice layer, which remembers, largely ammonia and methane. And then our rocky cores and their proportional sizes as well. Quite a bit of variation, actually, right? So, although we definitely justifiably group these all together, once we get into it, we can kind of see that each of the Jovian planets does play its own role. They've all evolved differently, largely based on their different sizes, and thus have different proportionalities. The density absolutely increases as we move towards the core. No surprise there. And it does because what we're talking about is differentiation. I said that a minute ago, but that's what has occurred in these planets that explains the layers. These planets are fully differentiated, just like all planets, and just like the terrestrial planets. Of course, the materials are different, right? The building blocks are different, but the differentiation is still there. Their total densities, okay, we summarized here. We see that Jupiter and Uranus are about identical. Saturn stands out because it has such a low density. The only planet that can float. Get a big enough bathtub, you can float the planet of Saturn. And then the answer is already given here. What molecule was the main component of the primary atmosphere of the terrestrial planets? Also hydrogen. Same primary component of the gas giants, the Jovian planets. Same primary component as the sun, right? It's the most abundant molecule, most abundant element in the universe. Remember, this was the primary atmosphere of every planet in the solar system. The only difference is that every time we talked about the terrestrial planets, we always said the primary atmosphere got lost right away. That's because of the location of those terrestrial planets to the sun. We will touch on this again in chapter 13, I think, 13 or 14. But for now, I think that's a totally, reasonable explanation, is that terrestrial planets were just too close to the sun to hold on to their primary atmosphere. The Jovian planets were far enough from the sun to hold on to it. They kept their primary atmospheres. And in doing so, they were able to pull in more hydrogen and get as big as they did. And in the process, get the other characteristics that we can see that they have: the large size, the layers, and the consequences of all of that, such as the magnetic fields that we're just about to talk about. So it all fits together nicely, and it all is a cause and effect that they, simply put, were able to keep their primary atmospheres. That's, what we still see, right? The proportionalities still are still there. Why did they keep them? Well, had to do with the distance from the sun. And, I said that, I kind of said that with a caveat. I said, oh, it's a sufficient answer for now, right? Because it's this chain reaction that they're able to keep them in the first place because they're far away, but then they can then continue to keep them because they're able to pull in all the extra gas and get bigger. So it ends up being, I won't check the chat, but hopefully if you want to venture an answer, you've had a chance to. It's the combination of the large mass and them being cold. However, if this is a, kind of a chicken and egg situation where it's hard to say which one came first because one leads to the other and then just continues, right? You need the chicken to make the egg, you need the egg to make the chicken. Well, you need cold conditions to pull in enough mass to become large, but then you need to be large in order to continue to pull in enough mass. So, which is kind of like the start of this reaction. I guess you could safely say it's being cold. You couldn't start to get a large planet and have it become a planet with enough gravity to really sustainably hold on to the primary atmosphere if it wasn't cold in the first place. The conditions need to be cold. And cold, interestingly, here really means far enough from the sun. And it's not, you might just, it's really easy to think. And I don't want to get into it because we'll have an opportunity to do it later. But it's really easy to think that in space, it's always cold. And that's just not the case when you're near the sun. If you're protected from the sun somehow and you're in space, then sure, absolutely. It's a vacuum of space, it doesn't hold heat. So things just, radiate their heat and they just cool, right? But as if you are seeing the light coming from the sun and you're, Earth distance away, that is a lot of energy hitting you. And therefore, you get baked in space while also simultaneously freezing, and depending on, what side of you faces the sun. So the light intensity is really significant when you're in an inner solar system. So in that respect, space is, really hot and really cold simultaneously. It's cold in the sense of, not insulating, but really hot in that incoming light. But if you get far enough away, that incoming light argument can start to be changed, and then you get to a type of space that is unequivocally cold. And that's what you need for Jovian planets. Okay, that's all I'll say for now. And just being large, just in radius, right, would if you were just big but not more massive, it'd actually be easier to lose things because the gravity would become weaker. If you had, if you swelled up a planet but kept its mass the same, well, now the upper layers would be very, easy. They'd be very easy for them to escape into space. So that this they crossed this one out because they said, well, this is like the opposite effect. Just being big without being more massive would never be good for holding on to any type of atmosphere. And of course, the primary atmospheres are the hardest atmospheres to hold on to because they're made of the lightest elements. So, as a reminder, here are the escape velocities, by the way. These are the current escape velocities. I mentioned that because I talked a lot about this sort of this evolution, right, of atmospheres. The slides have too. And I've hinted at a lot about the conditions that allowed the gas giants to be formed in the first place. So hold that thought for now and instead just focus on what are the gas giants like that they managed to make it. They got big enough fast enough. They held on to their primary atmospheres and then got bigger and bigger and now have these huge masses, which means they have very large escape velocities. So now they are really safe in terms of their atmospheric retention. They've reached a very stable state in terms of how much that hydrogen atmosphere they can hold on to. And we see that with these numbers. The escape velocities for Jupiter, Saturn, Uranus, Neptune are really significant, right? 60 kilometers per second, 36, 21, 23. In comparison, Earth's is around 10. right? So 6 times greater on Jupiter for its escape velocity. So no way could even hydrogen, right? The easiest, not, I guess not the easiest as diatomic, but still a very easy gas to escape. No way can it escape under, most temperature conditions. And if we look at the temperature conditions, because they are fairly cold planets, we see that the difference between them, right, the average hydrogen speed in the upper cloud layer of Jupiter compared to the escape velocity is not even a fair comparison, right? Hydrogen has no, in the sense of that hydrogen has no chance. There's no way it's going to escape. 1.2 kilometers per second is it's at, how fast it's bouncing around just by, random probability and because of the heat energy. And this is how fast, 60 kilometers per second, it would have to be going in order to escape into space. Well, there you go, right? That is a big difference. It's just not going to happen. All right. So if the planets all just held onto the primary atmospheres and still have essentially, that composition of mostly hydrogen, right, with a little bit of helium as our primary atmosphere, right? So about 6% helium, 94% hydrogen. Why do they have such different colors? Well, really, it just comes down to fairly trace amounts of molecules in their upper cloud layers that give their colors. So methane and ammonia are the big contributors to the colors of the cloud layers. And even though the numbers for Jupiter are so small, they don't even show up as percentages, they still help define the colors. They're more, and we have more significant amount of methane in Uranus and Neptune. So just to kind of focus on that, as because otherwise there's a lot of things to sort of keep track of. Just remember that these numbers, so non-trace, so significant amounts of methane, are what define the upper cloud layer characteristics and therefore the color of Uranus and Neptune. Because there's so much methane, they look bluish. Both of them look bluish. All right. Uranus is a real faint blue, and if you some older visible light images of Uranus are kind of always represented as more like a yellow color, but more accurately, it does have a faint blue color to it. Neptune has always had a richer blue color, but you can see that in both cases, it's, oh, I'm telling you, it comes from the methane, and you can see reasonably that, that number does stand out. There's not much methane, in Saturn. There's some, but the colors of Saturn are going to be defined more by a combination of methane and ammonia rather than just methane itself. Okay, so we can then say that the clouds, the defining clouds for Jupiter and Saturn are frozen ammonia clouds, and whereas clearly and in really large percentage, the clouds for Uranus and Neptune are frozen methane. And the colors are caused by the chemical reactions in the atmosphere. So what other larger molecules are created based off of ammonia and methane? And also, what those molecules do, right? How they release light through chemical reactions. Okay. This is the temperature of the cloud layer, kind of a stand-in for the surface sometimes if you just like quickly think about it, because it's of course the part that we see. But it's really best to call it the upper cloud layer because it's not a surface of anything. And we can see what the temperatures are like. Cold for Uranus and Neptune, all cold, right? But big difference. Methane freezes at 91. And so you notice that 91 is sufficient, in other words, the temperature of Uranus and Neptune, of the cloud layers of those planets, is sufficient to freeze methane, but not to freeze methane on Jupiter and Saturn. Jupiter and Saturn are too hot to have frozen methane in their cloud layer. So now a different story is their rotation. I said it's fast, right? They spin really quickly. They get part of their formation because they pulled in all that gas. In doing so, they picked up a lot of speed as that gas got pulled in. Sort of like, it's like this like spiraling effect, right? And it's like all that matter's coming in is just making them spin faster. Even though their inertia is going up, that incoming rotation won out. And the rotation speed at the edge of the atmosphere, and specifically at the equator, so like kind of right at this point where the speed is greatest, is really significant. And it has real key characteristics in terms of what's happening with the clouds, the way they behave, the way they form bands the bands are explained by the fast rotation rates because that forces essentially the clouds into these band patterns. We don't see bands of clouds on Earth because the rotation doesn't dominate sort of the Coriolis effect in our own, global weather patterns, but it does on these planets. Their atmosphere is absolutely, dominated by their rotation speed. Just to kind of put it generally, it's a subtle idea, so you can only explain it so well, in a short amount of time. And so rotation rate, for this one, so all right, tilted this way, like this. All right, so these are all their, fast rotation rates, based on their short rotation periods, many thousands of miles per hour. And so this ties in with the concept of convection. Just as a quick review, convection is when hot air rises, becomes cool air, which is less dense. Notice, right? Compacted hot air. As it cools, the density goes down. As the density goes down, it is able to sink. It sinks back down because of gravity. It rose because it was expanding, but once it stops expanding, there's no mechanism to keep it rising. So then gravity takes over and it just sinks back down. And so that creates the convection cycle. And then this, on kind of a structural level, we call it a cell. So, it's a cycle in time, but it's a cell in space. So the cell is the name of the whole rotational structure, right? So if you take that basic idea of convection, happens throughout the solar system, we have it here on Earth in our atmosphere, and you combine it with really fast rotation that exists on the Jovian planets, you end up with these convection cells that are stretched around the whole planet. And that's what makes the bands. So the convection and rapid rotation conspire to set up zonal flow, and zonal flow is based off of the latitude. And Jupiter's light bands are from upward flowing warm gas, and the dark bands are from downward flowing cool gas. So each band corresponds to one part of this convection cycle. But then they just extend all the way around the planet. So it's kind of interesting, right? So it's like if this is the side view, well, we could just continue this all the way around to complete a circle. But still important for the other Jovian planets, but not as easily summarized. And to measure the atmospheric rotation of the giant planets, well, that's different than measuring the planetary rotation. And it isn't significantly different on Earth, right? Our atmosphere moves with the planet. And sure, there's storms and so on, but there's not a noticeable different rate of our atmosphere moving relative to the ground underneath. Well, that's not the case for the Jovian planets. They really have these atmospheres that are sort of sliding over those more solid layers underneath, and fully solid layers if you go deep enough, and behaving differently, right? So there's actually separate rotational rates for the atmosphere compared to the core. And if you wanted to track the atmospheric rotation, and hopefully you had a chance to answer if you wanted to, but I won't check chat, you'd have to track a single feature like a storm or something in order to find out how fast the atmosphere is moving. If you wanted to know what was going on with the interior, then you'd have to penetrate the atmosphere, like with a radio signal. And that way you could, figure out, using the Doppler effect mostly, you could figure out how fast the solid layers are behaving. And that matters, right? That gives us our rotation rate value. But it's important to acknowledge that the atmosphere moves separately. The animation is a little fast. It might make you squint or give you a headache or something to look at it. But if you do take a look, you can see, that there's some real interesting behavior here, right? And we can clearly see the different directions of rotation. And the upwelling dark bands, yeah, because it was so the warm gas dark bands from the downward, no, the other way around. So light bands from the upflow. So the upwelling light bands and the darker sinking bands flow in opposite directions. Like notice like kind of near the North Pole, you can see the direction of motion being one way, and then that light band underneath with some dark storms at the boundary between them, but the whole band itself moving the other way. So they're always shearing against each other, which is kind of why there's so many of these, rotational storms at the boundaries of these bands that are moving opposite directions. And that same opposite direction, it's shown up here. So see how the velocity is to one side of the dotted line at these different latitudes? That means that it's flowing, that band is moving towards the left. Whereas the bands here with spikes that are to the right of the dotted line, because this bottom axis represents wind speed, they're moving to the right? Or clockwise versus counterclockwise. And so that shows that different bands move in opposite directions to neighboring bands. And the interior rotates at a different speed entirely, than all these rotation speeds that we're seeing. Pretty fascinating system, honestly. Right? So this is just a little history about radio signals. We actually saw this before. We talked about how radio signals were discovered and how that led to the discovery of radio signals coming from the center of the galaxy. Well, early radio signals also were found coming from Jupiter, which led to the finding that Jupiter had a strong magnetic field. This is kind of showing some data for the strength of that magnetic field based off of radio wave measurements. And the image in the background shows the auroras of Jupiter. Also, a clear indicator of magnetic activity. This one here is showing the direction of the magnetic field, and then kind of showing the path of the solar wind coming in, just like on our own planet. To jump back to storms real fast, we got the Great Red Spot, which is a high pressure system, famous feature of Jupiter, stable over hundreds of years. It won't be around forever, but it has been around for recent human history. There are lots of other storm elements, as we saw. It's not just the one storm by any means. Saturn is known for its storms as well. We've got big vortexes forming, but no stable ones. That's not to say that there hasn't been longer stable storms on Saturn. The time scale, if they just last for hundreds of years, the planet's been around for billions. So who knows what's happened in the past, but humans weren't around to observe it. Saturn also has an interesting feature at its North Pole. It has this large hexagonal vortex. You can really see the shape of it, like this rounded edges hexagon. Circular at the very pole, but it takes this interesting shape. And there's some explanation based on fluid dynamics about why it takes that shape, but it's pretty cool. Neptune also has some storms spotted by flyby missions, such as Voyager 2. Not a lot of flyby missions on these distant planets. Case in point, Voyager 2, happened more than 50 years ago. We have some images of cirrus clouds of methane on Neptune. So there's cloud behavior. There are some storms. We don't see any of that on Uranus because it's just too cold. So Uranus doesn't really have enough internal energy to drive storms. We saw that its temperature is kind of comparable on the surface, but there's not its internal temperature is much less. And that may have something to do with why Uranus is on its side. It's thought maybe there's a major collision, a lot of its internal energy was released, and it makes its surface just totally still. Almost no movement. It's really like it has like a frozen crust on it. Going back to magnetic fields, because we started touching on them. This is the region around a planet where the term magnetosphere, which we use a lot when we talk about magnetic fields, well, that's the region where the planet's magnetic field is the dominant magnetic field. If you go past a planet's magnetosphere, you enter the sun's magnetosphere. You'd have to leave the solar system to leave the sun's magnetosphere. In terms of which planets have magnetic fields, um, there's an X above Mercury, but we learned that it does have a weak one. Venus has an induced magnetic field, but not an internal one. Earth has full-on internally created intrinsic magnetic field. We've talked about it. I think there's supposed to be a check mark here. Mars doesn't at all. No magnetic field, induced or otherwise, intrinsic or induced. But then all of the Jovian planets have strong magnetic fields that are all created in their interior. So they all have magnetic fields that are, in many ways, most similar to Earth's, but in other ways not. But at least in terms of that, they're all created internally. They're all fairly strong. In fact, they're all stronger than Earth's magnetic field. So, if we're thinking about the planets that have magnetic fields, it would be, the five would be the Jovian planets and Earth. As we learned, Earth's is almost aligned with the poles, although the names don't match because, of course, the magnetic South Pole is the geographic north, causes auroras, helps with harmful radiation, right? Helps protect our atmosphere and protect the life within it. On Jupiter, there's also a magnetic field that's fairly well aligned with the rotation axis, but more significantly tilted at 10 degrees away. Also, it's flipped. Okay. So the north actually points to the geographic north. So the North Magnetic Pole is also the geographic North Pole. So, and I want to mention this because, we talked about this kind of hypothetical idea for Earth. So that means if you went to Jupiter and you wanted to use a compass and you got out a compass while you're, sailing around the clouds of Jupiter and you looked at that compass and you read north, well, it wouldn't take you north, right? Your compass, if it reads north, means you're heading south. So that's the whole issue, that you have to remember to go the opposite way that the compass says, with the marginal upside that at least now the poles agree. The geographic and magnetic poles agree. But it's a pretty weird thing that now you'd have to remember to go the opposite way if you actually wanted to go north or south. There's Aurora again. Saturn, Saturn is tilted. Jupiter's not shown tilted here accurately. Here's Saturn with its axial tilt, but then relative to its rotation, the magnetic field is aligned. And so that's almost like Earth, right? So sure, Earth has an axial tilt relative to the ecliptic plane, but then our magnetic field is not tilted relative to our axis. Well, likewise for Saturn, right? So well aligned between magnetic poles and rotation axis. There's the auroras of Saturn. Uranus has a strange magnetic field. It is really significantly tilted from the rotational axis of the planet, and it's not even at the center of the planet. And you might think, well, maybe that's just because Uranus is already very strange with its own tilt, being essentially knocked on its side after all. But that idea of having a huge tilt between magnetic poles and rotation axis shows up again with Neptune. So it's not just Uranus. Maybe the angle's not as big, only 46 degrees off, but still pretty significant. Furthermore, the center of that magnetic field, again, is nowhere near the center of the planet. It's in both cases, it's near one pole or the other. So what could be driving such a thing? How do you create the magnetic field? Well, the magnetic fields of Jupiter and Saturn are thought to come from that metallic hydrogen, that kind of hopefully set the stage for that when I talked about its ability to conduct electricity. So it acts as the electromagnet. What does the what is the electromagnetic stand-in for Uranus and Neptune? Well, it's not as obvious, although a lot of, current studies and good theories and confirming measurements have really pointed to that it is the ice, the much thicker ice layer. There's ionic versions of the ammonia and methane ice that certainly could act as the conductor. So there's other ways to conduct electricity other than metals. Salt water can conduct electricity okay. And so, that being kind of an ionic fluid. So that's probably what's happening with Uranus and Neptune. Why it's not centered, because after all, the ice layers, create a shell is not entirely clear. What about it creates these concentrations at poles is definitely an open question. Right? So now what's their role in the solar system? They make up most of the solar system in terms of its space. Right? If you think about the orbits of Jupiter to Neptune, these Jovian planets really dominate the volume of the solar system in a sense, right? Because they're so spread out. And if you compare all the terrestrial orbits, they're just all squeezed in near the sun. So from a bird's eye view, most of the system is occupied by the orbits of these big planets. Neptune has a great historical um, discovery story. It's the only planet that wasn't known to ancient people. So, in the 1980s, I would have said that was also true of Pluto when Pluto was classified as a planet, but now we know it's not. Justifiably, it's one of many dwarf planets. Obviously, you can't see Pluto with the naked eye, but you also cannot see Neptune with the naked eye. There's no way to observe it. Uranus is rather difficult to see with the naked eye. You need ideal conditions, but those would have more readily existed before city lights, right? And so, ancient peoples throughout the world knew about Uranus as one of the wandering stars, later identified as a planet. Basic telescopes made it easy to find Uranus, more brilliantly, but not Neptune. Neptune was still too faint to even see with telescopes well into the 1700s. It wasn't until around 1750 that astronomers were able to confirm with direct visible confirmation looking through a telescope lens that Neptune was there. They had to, build much better telescopes and bigger ones to do so. But before that, it was suspected that Neptune existed because of this. It was believed to exist since the 1500s, so about 200 years up to its confirmation with the telescope, because of the orbit of Uranus. It was noted with careful observation and measurement that Uranus's orbit seemed off, that it was being pulled on by another mass. And of course, it was pulling back on that other mass. And so then it was speculated there had to be another large planet further out. Indeed, there was. And this works, this idea is based off of none other than Newton's law of gravity. And so that's going to change the orbit, going to cause these small perturbations. And because they're going to be more pronounced when the orbits line up, right? And so these perturbations change over time as the alignment of the planets do. And they're subtle but measurable. When Neptune was first confirmed, since it was confirmed by a astronomer in Great Britain in the 1750s, which was part of the Royal Society, they named it after the current King of England. And so it was called Georgia, named after King George. But the name did not stick. That's a fun fact. Neptune used to be named Georgia. So, seasons on Earth, we know this. I assume we know. Tilt of the Earth's rotation axis, right? Reasons for the seasons is axial tilt. So, do the Jovian planets have seasons? In some cases, yes. Would you expect Jupiter to have one? No, Jupiter's too straight up and down, right? Any planet without axial tilt is unlikely to have seasons unless it has an elliptical orbit, and Jupiter does not. Remember, its rotation period isn't too long, so it would take 6 years to go from, one, basically perihelion or aphelion to the opposite. The way to think about it is, one hemisphere relative to the equator slightly tilted towards the sun and slightly tilted away. So like a northern hemisphere summer and then a northern hemisphere winter, maybe. I think that's the way the tilt is, right? Because it's so tiny. So 6 years, 12 years for the whole orbit, right? But almost no change in solar flux because of that straight up and down axis. Saturn would, though. Saturn has a significant tilt, right? But it's 15 years and the distance is pretty great. So there's definitely a change and a significant change, but a change compared to a small amount of energy in the first place. All right. So the change may be similar, but the total energy is so much less that the seasonal variation is consequently very small. And so that means that we don't really see any evidence of seasons on these planets. And this would be the last candidate that would really be a reasonable candidate for having seasons, because as we get out to even further distances, we'll skip over this. So as we get out to Uranus, which has pretty interesting axial tilt, well, it I guess if the axial tilt wasn't so dramatic, we would just say, absolutely, there's no the light is so small that having even a big change in a little thing isn't going to cause an effect. And that is true. I'll skip to Neptune, so at least make this argument clearly that Neptune definitely, despite its axial tilt and a significant change in the solar flux on the different, hemispheres, there is just so little energy that there's no evidence of seasons. So similar changes, but again, tiny change overall. It's just this Neptune is so far from the sun that the light just isn't that intense. Still much more intense than starlight or moonlight or something compared to Earth's moonlight, but still just not enough to drive seasonal variation. But Uranus, on the other hand, because it's tilted all the way, and you have these extreme cases where you have many Earth years of total darkness at one pole, and then many Earth years of complete light at that same pole, half an orbit later, you might think that, okay, well then, Uranus can have some significant change in the amount of energy that's hitting the different poles. Um, the time it takes to do that is pretty dramatic, right? To go from this orientation to this one takes 42 Earth years. So not an easy thing to study, right? So extreme changes, right? So darkness half the year, half the Uranus year, but the overall like data to show what that's doing to the planet is still coming in. We have to measure a few cycles, and that's going to take quite a while, right? Considering how long it takes. All right. So that will wrap things up. Yeah, it probably does, Maxwell, have seasons, you know. Um, so even though I say like the study is ongoing, that there has, that we have been, looking at what effects this has on the different poles, how, one pole is just, able to heat up for many Earth years. And I don't know exactly what the results have shown, but certainly that pole gets a lot hotter. What that means, I'm not sure. Especially with Uranus being the way it is, with having this almost inert surface, that might make it easier to study variations. And it may just come down to there's what we need is a new flyby mission, or ideally send a probe out there to actually orbit the planet, like we sent probes to orbit Saturn, for example, and collect, months or years of data. But not top priority for NASA. I don't know if any other space agencies are doing it. So there you go. It's like We just need more space probes to answer interesting questions like that. It's totally reasonable to think there's a lot more going on.